My intent here was to try to revisit some of the recommendations, particularly in the energy supply sector report from the Michigan Climate Action Plan. And much of that will be really a local focus compared to the things that have already been presented. So I'm going to go through that pretty rapidly. And then a real general, sort of non-technical, hopefully, discussion of carbon capture and geological sequestration, again with specific focus here in Michigan.
So if you're talking something much more interesting than what I'm saying.
Well, if I can make this gizmo work.
Maybe aim this way.
This thing's not going to work, so. As I tell my students, make sure and give a punchline at the beginning, and that is that we can do it here. This is a technology which is especially available here in Michigan. And as such, as a geologist who knows a little bit about the subsurface here in Michigan, we've actually been in the middle of a very active research program. Okay, again, I'm going to go through this very quickly. Probably most of you have some familiarity with the Climate Action Plan. The initial charge from... Sure, yeah, absolutely. The original charge from the governor was premised, of course, on the idea that the scientific community is quite confident that greenhouse gases are causing Earth's climate change, and especially, I'm going to turn to my own little technology here, because that doesn't work. I just wanted to focus on the important recommendations for encouraging technology innovation and the adoption of policies that provide net economic and environmental benefits. So these were the charges that the governor has provided for us in the Climate Action Plan. And these are really just local representations of similar sorts of concepts that Skiles has presented. And these are emissions in Michigan, recent information, historic stuff, and reference case projected gross greenhouse gas emissions by sector. And you'll notice that a very substantial proportion of this, obviously, is fossil fuel combustion, gasoline use, residential, commercial, industrial fuel use, and of course electricity, which is primarily coal.
Jet fuel, is that like plain flights, or is that?
This is from the council's report, so I don't have much to say about all of this. This is the truth as far as I understand it. Maybe the important thing to point out to you here, their last factual information about 2005. Notice the emissions are about 250 million metric tons. Keep that number in mind. 250 million metric tons of CO2 emissions in Michigan. And notice someone asked about what the projected increase is. And of course, remember, projections are just what people believe is going to happen. Who knows what's going to happen? Next one, please. And just to focus in on the energy sector in particular, and this is the electricity sector in Michigan, keep in mind that the blue here is emissions, again, millions of metric tons of CO2 equivalent, primarily CO2. Notice that the blue portion here is coal combustion, that is in-state production, and the pink is imported electricity produced primarily from coal from the Ohio River Valley. So we could say that essentially all of this, well, except for the blue, which is natural gas, essentially all of this CO2 emissions. Again, keep in mind the numbers. About 2005, about 90 or so million metric tons of CO2 emissions in the last real historic records. And these are the projections for increases here in Michigan. And this is, of course, the Climate Action Plan recommendations. Historic and projected. This is business as usual, or the reference case, and this is the recommendations based on the Climate Action Council's projections, and this is what's suggested. So the recommendations, of course, are a little bit better than what the projections of the council has provided, or vice versa. And this is inherent in many of the things that Skiles presented to us. That is the idea of stabilization wedges. From a national perspective, these folks from Princeton a number of years ago simply made it clear that we have to do everything with pedal to the metal as fast as we can, and that a series of contributions to decreasing greenhouse gas emissions, of course this is greenhouse gas emissions here on the left, this is calendar year, and this is the projection off into the future. And we hear lots about the potential for increases in low or no greenhouse gas emissions technologies. But keep in mind that this blue portion of this diagram, where we're doing a slow, steady, and then decrease of greenhouse gas emissions, this is what we're going to need as far as emissions are concerned in order to ensure, or hopefully produce, greenhouse gas concentrations in the atmosphere that are below the 500 parts per million threshold that we believe will bring about dramatic climate change. And by the way, unfortunately, some of us believe that at 380, which is what we're currently at in terms of concentrations of CO2, that we are already reaching a tipping point. So this is a fairly optimistic projection. But again, the important point here is a bunch of stuff has to be done. And regardless of what we do, there's still going to be a continued significant reliance on fossil fuels. And this is a little more specific, an international perspective for the International Energy Agency. And the main focus here is here's all of our wedges. This is the standard reference case or baseline or business as usual. And this is where we need to get at some certain time period. And what I wanted to point out here, at least from an international perspective, there's the suggestion from thoughtful and well-intentioned folks that at least 20% of the emissions reduction or emissions mitigation technology is going to come from carbon capture and sequestration. And again, you can't see this terribly well. And again, this is just a projection. This is from the Energy Information Administration. This is the federal government DOE-based information. And this is historic to the left of the black line, and this is projections. And again, this is just what some fellow believes, and I understand this guy's mainly a statistician. But at any rate, the point that's important here is that non-fossil energy use may grow very rapidly in the coming years, but fossil fuels are still going to provide a very substantial proportion of energy use in 2035. And this is just my little quote here, and that is rapidly transforming U.S. fossil fuel intensive energy infrastructure to low or no greenhouse gas emissions infrastructure on the time frame that's really necessary to address climate change is a very formidable challenge. That is really an undeniable statement. Okay, next one, please. And of course, this comes down, can we really wean ourselves of use of fossil fuels and the associated greenhouse gases? Can we really do it in this absolutely critical transition period of 30 to 50 years off into the future? This is the significant transformation period, this transition period. Okay, next one, please. And just a couple of quotes from the Energy Supply Sector Report that in Michigan, I'm trying to sort of drill down here to Michigan specifically. While the age of Michigan's coal-powered electric fleet is one of the oldest in the country, in excess of 50 years, that really constitutes a bit, it's a bad thing obviously, because it's old, truly dirty coal technology, but it's kind of a good thing because it gives us the opportunity for at least retrofitting, if not replacement, of these this generation capacity with a much more feasible incorporation of carbon capture and sequestration. Just a few more quotes here. I don't want to overwhelm you with these, but some of the supply sector recommendations were that advanced, that is fossil fuel-based electric generation technologies, pulverized, fluidized beds, et cetera, and sequestration, that is with geological sequestration, or reuse of carbon that's captured from plants may have the potential to materially lower CO2 emissions that are associated with fossil fuel electric generation. Some of the recommendations further in the report were that Michigan should initially encourage enhanced oil recovery using CO2 to enhance the recovery of oil from depleted oil fields, which would be accompanied by modest sequestration of carbon dioxide, modest in terms of volumes, and that this sequestration and especially production of depleted oil from depleted oil fields should be initiated in the next 2 to 5 years. This is a very highly accelerated program here, so we've got to start thinking about this stuff very quickly. And finally, in terms of extracts from the report, the suggestion was that by 2015, that's only 5 years off, folks, Michigan should encourage and support additional pilot and demonstration activities for deep carbon geostorage in several locations in the state. That's 5 years off, and we need to be doing this stuff, okay? Not just thinking about it. Right? And finally, by 2020, Michigan should have the robust legal and policy framework that's consistent with national intent that enables full-scale industrial carbon geostorage capabilities. So the report has really focused on the critical component of this technology for our greenhouse gas emissions approaches. Now, we'll talk a little bit about geological sequestration, or geosequestration. This is, of course, the safe and permanent storage of CO2 in geological media, and that's key, right? This isn't necessarily something that can be done anywhere. This is something that's done based on the very careful site selection and due diligence consideration of all feasible uncertainty about the safety and permanence of storage. And of course, the intent is to reduce anthropogenic greenhouse gas emissions to the atmosphere. This little schematic, of course, shows the CO2 point source. This technology is really only appropriate for large industrial point source emissions of CO2. The capture of that CO2 and separations Carbon dioxide has rather distinctive properties in that at relatively low temperatures and pressures, it can be turned into a supercritical fluid, which has a drastically decreased volume, drastically increased density, such that the efficiency of storage relative to other emissions, nitrogen, water vapor, etc., is greatly enhanced, so that the compression of the CO2 to about 1,100 pounds per square inch, about 100 times the pressure of a racing bicycle tire. The transport, preferably to local disposal sites, and where I come in, the only stuff I really know a whole lot about is the CO2 injection and storage in deep underground formations. So the compression, transport, and injection are fundamental components and potential sources of expense for the sequestration technology. Please. And again, this is a little bit light here of the various geological media or contexts in which geological storage can be undertaken. The three that are most relevant to Michigan are one, injection into underground depleted or exhausted oil fields where known storage and retention or proven storage and retention from the oil and gas that was previously stored in those reservoirs is known. Second alternative is the injection of CO2 into reservoirs which have some remaining oil, such that the increase in pressures in those reservoirs enhance the production of the petroleum to the surface. And the CO2 also has properties which enhance the flow properties of the petroleum. And finally, the injection into saltwater-bearing, unpotable, non-potable waters in the deep subsurface. And notice the scale here. Again, the minimum depth in the subsurface that's required for this, this approach is about 1 kilometer in the subsurface, because the compression of the CO2 into this high density, about 70% the density of water, supercritical state, requires that the compressed CO2 be injected into subsurface formations with ambient pressures sufficient to retain that CO2 in its supercritical state. So we're not talking about injection into shallow deposits, but rather considerable depth, at minimum about 1 kilometer into the subsurface. Next one, please. Okay, just some review of key factors that are required in this assessment of sequestration. Certainly storage capacity. What is the volume requirements for an anthropogenic CO2 source? For example, large coal-fired power plants generate on the order of 4 to maybe as much as 6 million tons of CO2 per year. A 50-year design life would then result in 50 times those numbers. So we've got to think about local disposal sites which have sufficient capacity for those kinds of volumes of source. The pore volume, the area, the pore volume meaning the tiny microscopic void spaces between the mineral grains and the subsurface rock formations. Remember, these aren't big swimming pools underground. These are really rather microscopic void spaces between the mineral grains and the rocks. The area that those suitable rocks are distributed in, of course, the temperature and pressure that is sufficient depth to retain the CO2 in this dense supercritical state, again, below about 2,600 feet or a kilometer or so. Injectivity is fundamental, the ability to inject the CO2 at sufficient rates to make this an economically viable undertaking, and not increase the pressures in the bottom hole to the point where rocks begin to fracture. And this is a function of rock properties, which is why us geologists are so involved. Permeability, porosity, and thickness of the formation. How much of an interval can you actually inject the CO2 in a borehole? Containment and security are obviously a fundamental aspect of this entire initiative. The fact that you've got an impermeable seal, just like the cap rocks or seals in petroleum reservoirs, and that this, the seal and the other components of trapping this buoyant CO2 are suitable for the CO2 on the scale in the areas of interest. Again, site details, technical economic viability, how far do you have to transport by pipe, how deep do you have to drill, etc. And the last one, of course, is a fundamental requirement, is that you can't interfere with existing natural resources in the subsurface. A little bit of geology now. Michigan's deep geological sequestration injection zones. We, for the last 4 or 5 years, have been working with the Department of Energy in the Regional Carbon Sequestration Partnership Program, the RCSP program. One of the most recent results of this effort, the largest of the federally funded programs for evaluating carbon capture and sequestration. One of the most recent products has been this Atlas of Carbon Sequestration in the United States and Canada. Our university has been a contributor to through this atlas and continuing activities. And one of the principal reasons that Michigan is such an appropriate site for geological sequestration is simply because it's a very distinctive geological setting relative to the United States, North America, the world, in that we have as much as 16,000, this is the way geologists represent rocks, a bunch of stacked layers. Think of looking at the sides of the walls of the Grand Canyon. We've got as much as 16,000 feet of sedimentary rock strata below our feet, at least in some locations in the state. Almost 3 miles of the suitable sorts of rocks for sequestration available. And I've distinguished 3 different target zones, rather than using the geology words that none of you will recognize: shallow, intermediate, and deep. And we'll talk very briefly and give you some very simple diagrams to try to represent the relative scales of potential for injection that these formations provide. We used methodologies that have been standardized in the Department of Energy's approach to the characterization of sequestration potential in the U.S. Next one, please. This is not really quite accurate. I took it from some students' work and he didn't quite get it right, but it gives you the general idea of large stationary CO2 emission sources in lower Michigan. And maybe we can distinguish the southeastern portion of the state, the central portion of the state, northern portion of the state, and the western portion of the state. So these are regions that need to be considered somewhat distinctively with respect to the potential for geological sequestration. Geology is not the same everywhere. Next one, please. Get a little light here, but if we consider the shallow reservoirs, injection targets, and confining zones, I'll just use these words: Bass Islands in Sylvania. These are words for rock formations in the subsurface. And the next one, please. A recent, within the last 3 years, this Midwestern version of the Regional Carbon Sequestration Partnership funded by the Department of Energy. It's a 9-state partnership. Following a phase 1 study in which national consideration of sequestration potential was undertaken, a second phase was commenced in which relatively small-scale injection demonstration projects were undertaken. And one of those projects was undertaken in northern Michigan in Otsego County. And just a very quick summary of the results of that investigation in the next one. The results of this pilot CO2 injection test: they actually drilled a well, injected CO2, and evaluated with many, many sorts of monitoring procedures the results of this relatively small-scale injection test. 20 days of CO2 injection, about 10,000 metric tons. Remember the scale of emissions we talked about earlier, millions of tons. So this is a very small amount, mainly because the pipeline capacity, the available CO2 at the site was relatively limited. If we annualize the injection rates, we would very confidently predict we could inject as much as 200 or so thousand metric tons per year. And based on some other data extrapolations and considerations, somewhere in the order of 500,000 tons of CO2 could reasonably be injected into one single well. If we consider the scale of industrial CO2 emissions, I said 4 to 6 million tons, we're talking about 10 wells could accommodate the emissions from a large industrial CO2 point source. This was such a successful experiment that an additional 50,000 metric tons of CO2 was injected and additional tests are being conducted. Next one, please. This is some geology mumbo-jumbo. Let's just go to the next one. Basically, what I want to show you are a series of maps that we've generated showing, and let me highlight for you, the statewide storage capacity. And again, keep in mind these numbers, right? 5 million tons a year from a big coal plant for 50 years, 250 million metric tons of CO2 emissions. Okay? We've got a rock formation, which is a relatively small potential target. It's got 1.5 billion tons of CO2 sequestration potential in the state. The scale here, county by county storage capacity, high is 60 million tons in some of the northern counties. So this is a very prospective reservoir in the northern parts of the state. Next one, please. One of the other injection targets here in central Michigan, Sylvania sandstone. Not that that's terribly important. Again, let me focus you on this total storage capacity. And this is using only 4% of the void spaces in the rocks for various reasons. The standardized methodology for confident evaluation of storage capacity suggests that a small proportion of the pore space is actually available. But considering that, almost in excess of 700 million metric tons of sequestration capacity exists here in central Michigan, a very laterally restricted rock formation. Again, the scale of high storage capacity to low. Green is good, red is bad. Another potential injection target in central Michigan. Next one, please. If we look at intermediate, this middle zone, which is primarily petroleum reservoirs in the state of Michigan, this would be the Niagara and Reef reservoirs, both in north and south parts of the state. We've got confining layers and CO2 enhanced oil recovery targets. Next one, please. Just point out a couple of things. Over 450 million barrels of oil has been produced from this formation. The northern Niagara and Reef trend, this is a map, a bubble map of wells, oil-producing wells in the northern part of the state, gas-producing wells in the northern part of the state. So a significant economic resource of oil production has been produced from this especially appropriate enhanced oil recovery target. Next one, please. Just some initial considerations of enhanced oil recovery potential. As much as 100 to even as much as 150 million barrels of petroleum may be produced through CO2 enhanced oil recovery, and storage capacities on the order of these numbers. One more example and we will be done. The deep sandstone injection confining zones in Michigan. I won't worry about the formation names, just cut to the chase here. This is sort of the 800-pound gorilla. Almost 30 billion tons of CO2 storage capacity, focused really here in southwestern Michigan, although some recent investigations would indicate substantial increase in capacity here in southeastern Michigan. And remembering the distribution of sources, this is pretty significant. I think that's all of it. Just a quick acknowledgement to Congressman Fred Upton and his staff for support from a congressional earmark for some of our work. And thank you very much for your attention.
Do you have any questions or comments?
I just have a question.
Sure.
Is it your sense that the costs of doing carbon sequestration would mean that it's much more feasible because of economies of scale in larger coal plants? In your map of Michigan, you're probably showing the J.R. Campbell plant and the Cobb plant, and not the little 45 megawatt Holland plant. So the drift of my question is it wise for a small power plant to think about doing carbon sequestration? Or does doing that point us in the direction of mega-sized power plants?
Now, there's others in the room that may be better equipped to answer the question, but I think all of our discussions here are fundamentally based on the cost of carbon. Anybody doing business and generating electricity, if your cost for emitting carbon results in the need to mitigate those emissions, then whatever the scale of your operation, you're going to be incentivized to dispose of carbon. And smaller volumes of disposal require less or result in less uncertainty for the potential. I mean, there was a potential plan for emission or CO2 sequestration in southwestern Michigan associated with a municipal power plant in Holland. I mean, you could have done that with both hands tied behind your back. It was such a small emission source with such a gigantic resource that they could have taken CO2 from other sources, or that region could be almost, not that that would be feasible, but almost a net import of CO2 because of the sequestration potential. I'm not sure that your question, the answer to your question is no, I don't think it's a scale issue, although others may be in a better position to answer that.
Sort of nosily interventionist. I wonder if some of those, I see sort of a battery of utility and sort of governmental folks. Is there anybody else who'd like to comment on?
Well, I agree with Dr. Warren. Especially in these early years. I mean, small scale type projects will be very good to show that you can do the large scale projects. So I think that's one of the big advantages of doing, stepping up from these smaller scale is, you can inject, you don't need as big of an area, you don't have to, have as much monitoring going on. You can tell whether it's moving. And so I think early on it's especially good to do the smaller ones.
It'll be necessary, essentially.
I just had a question. Do you know of any, is there any research on public opinion or public acceptance of this type of technology?
Well, one of the fundamental aspects of our research program is public education. There's a sense that there's these mysterious problems with injecting fluids into the subsurface. We've been doing it for decades. There's billions of tons, billions of gallons of hazardous waste, very nasty stuff that's been injected into the subsurface. And the oil and gas industry injects tons of stuff. I mean, they extract huge amounts of fluids out of the subsurface. Really, it's a public education challenge. In fact, it may even be a steeper hill to climb than the technical challenges of sequestration. So your question is a very good one. It's a very significant component of this initiative.
Is the carbon dioxide inert then when it gets down to the?
Not exactly, but you don't have time to talk about that right now. Not exactly, but there are things that, like all of this, it's due diligence. How careful are you in understanding the subsurface environment? Understanding that you just don't know everything. I mean, if you're moving fluids that, miles away from an injection point, at some point you just really don't know for sure what's going to happen. For sure, you can have high confidence in what's going to happen, but you just can't be sure. There's a lot of other things we can talk about in terms of inert or not inert about CO2, but perhaps not right now.
Anybody who hasn't asked something? Yeah.
I just had this immediate visceral reaction when I saw Southwest Michigan and Lakeshore and sequestration and, you're talking about public opinion and public education. That was just my first initial response. Oh my gosh, how safe is that? And you're going to put it right along Lake Michigan.
It's at Lake Michigan, 5,000 feet below the surface, okay, almost a mile, more than a mile below the surface, with many, many layers of totally impermeable rock formation. So that's the public perception concept. We as humans sort of have a difficult idea understanding a mile below the surface and what's happening. I mean, there have been literally billions of gallons of very nasty stuff pumped into this Mount Simon Formation in Holland, Michigan. Okay, I don't know if you want to know the details. Now, and I think that that's a perfectly safe thing to do. It has been regulated from the get-go. There's EPA and state agencies that are very focused on the safety and security of those activities. A little bit different than pumping CO2 for a variety of reasons. But it is a public perception issue. And the fact that you're injecting materials adjacent to the lakeshore is really no different than injecting it anywhere else in terms of hazards. You don't want that stuff coming out of the ground. The objective is to make sure that it doesn't based on a geological assessment.
Do you have can you give us a sense of what this would cost in terms of kind of CO2 or something of that sort?
Currently, and again, there's others in the room that may be better positioned to answer that, something on the order of 30 or so % increase in electric power costs if you focus on electric power generation, coal-based electric power generation. The objective of DOE research activities is to decrease that to 10 or 15%. I'm not a good person to talk about those details. I'm a geologist, vanilla ice cream geologist.
I don't think you're really a geologist. Okay. Thank you very